I'm Donn Thompson, Director of Market Strategy and Positioning for the Portland Cement Association. This presentation is a summary of results of comparative life cycle analysis research on building materials for single-family, multifamily, and commercial structures done by the MIT Concrete Sustainability Hub. Past building environmental analysis has often been limited to an examination of only embodied energy, or only a consideration of a portion of a particular phase. They all represent limited approaches with no consideration of how products can impact energy and emissions during the use phase of buildings. They only provide a partial picture of full impacts. They fail to look at the complete life cycle, and they can often stop at only the pre-use phase. This is often described as a cradle-to-gate approach, where you're looking at limited environmental assessments leading up to the gate of the construction site. What the MIT study does is it looks at a more comprehensive full life cycle analysis, examining materials within a whole building context. So the study includes all phases of the complete life cycle of buildings, starting with the acquisition of materials and manufacturing during the pre-use phase, then moving to the use phase following construction to look at environmental impacts of operating energy and maintenance, and then in the end-of-life phase, looking at demolition and determining what products would be landfilled and what products are recycled. It attempts to be the most comprehensive and transparent buildings LCA to date, striving to provide full transparency, allow for ease of replication, to provide the development of an open and repeatable LCA process for buildings, to set precedent for the complete LCA of future construction. Basically to allow all others to replicate this study and to be able to use a full life cycle analysis in the future. The comparative environmental impacts were centered on two climates. One, a heating climate, Chicago, a second, cooling climate in Phoenix, Arizona. Building design and finishes were identical. The buildings were all designed to meet model code or current code requirements, and only the impact of the structural system or the exterior wall assembly was different. And in all cases, we were looking at a typical 60-year service life. 60 years is a widely accepted analysis period for LCA buildings, having been used for other environmental codes and standards. The study relied on objective data using US Department of Energy benchmark models of three building types: single-family residential construction, multifamily residential construction, and commercial construction. The chosen impact category was global warming potential. This is chosen because it's the leading environmental impact metric for policymakers and LCA practitioners. The study represents conservative comparative methodology. It's comparing concrete systems to best practice competitive systems. An example, best practice for structural steel recycled content. The study uses World Steel Association guidelines, which are an objective source of steel recycling criteria. 60% of recycled content for new structural steel assemblies is the standard that was used for the commercial study. And then at the end of the steel frame's useful life, 98% of the steel was assumed recycled. The goal is to be objective and to show comparatives in the context of real-world practice. So let's start by looking at single-family residential construction, comparing single-family wood frame to concrete structures. This sector is important because when you look at overall energy use in the United States, a full 40% of energy consumption is centered on the combination of commercial and residential buildings. Residential buildings alone consume 21% energy consumption in the United States. That's approximately 70% of overall electrical consumption annually and represents 40% of overall CO2 emissions. Buildings consume more energy than either the transportation, sector or the industry sector taken separately. And at the global level, building consumption, energy consumption in the United States represents 10% of overall worldwide energy consumption. The single-family market consumes 80% of total residential energy consumption in the United States each year. So it's an important sector to consider. What's interesting is that energy consumption has remained constant for about the last 30 years. There have been reductions in the energy consumption for heating and cooling because building code requirements have become more stringent. But that's been offset by plug loads, which have increased because of more heavier use of appliances and electronics. So it's important to look for ways to reduce energy consumption by improving the performance of the enclosing envelope of structures. For the single-family LCA, we looked at typical residential construction, 2-story, 2,400 square feet, representative of typical residential construction in the United States over the last 4 years. In Chicago, we were looking at a 2-story structure over a full basement. In Phoenix, Arizona, we were looking at a 2-story structure over a slab on ground. The comparison is between wood frame and concrete. Only the exterior wall systems differ. The wood frame assembly features fiberglass band insulation based on code requirements, which in Chicago means a thermal resistance or R value of R20, and in Phoenix, Arizona, the thermal resistance requirement is R13. That was compared to a concrete wall system formed with insulating concrete forms, which is a concrete wall formed with a stay-in-place forming system that features expanded polystyrene insulation, which actually exceeds code requirements. In this case, we were looking at a minimum R value of 22. The study looks at differences between wood frame and insulating concrete forms based on the amount of insulation in each wall assembly and the potential impact of thermal mass in the concrete wall. The only difference between the homes is the method of construction for the exterior wall assemblies. This is important. The study does not include impact of the differences based on air infiltration. The comparisons in the study assume the air tightness is the same for both the wood frame structures as well as the insulating concrete form structures. So in other words, tight wood frame is compared with tight insulating concrete forms. This is an area that will be examined more carefully in future studies when more reliable data are available to more accurately assess these impacts. So let's look at results. Not surprisingly, when you look at embodied energy components and emissions, you're looking at 13% higher embodied energy emissions in Chicago and 14% higher energy emissions in Phoenix, Arizona. But the study also has determined that the embodied energy accounts for only 2 to 12% of overall global warming potential. As we looked at earlier, many LCAs stop here, and it's not the whole story. The best practice of life cycle analysis is to go farther and include energy associated with the operational phase. When we look at the operational phase of single-family residential construction, we see that concrete homes produce 5 to 8% lower greenhouse gas emissions than current code-compliant wood frame construction. The efficiencies of concrete wall assemblies result in the lower overall emissions. And since concrete homes are so durable, they can consistently last longer, so the comparative reductions in greenhouse gas emissions will continue to grow beyond that 60-year life cycle. In terms of total energy, the concrete homes use 8 to 11% less energy than code-compliant wood frame construction. By total energy, we mean combining the embodied energy with the operating energy for the full life of the structure. So now, based on that example, you can see the importance of considering the operating energy during the operational phase to provide a full picture of the overall environmental impact of a building material. As part of the key findings, the study looked to optimize performance of the concrete wall assemblies. One of the areas investigated was to look at supplemental cementitious materials, either fly ash, blast furnace slag, or silica fume as a substitute for some of the cement content in the concrete mix. The study assumed a 10% SCM content in the mixes studied, but by increasing this to 50%, you could see a 5 to 10% reduction in embodied energy emissions during the pre-use phase and a 3 to 4% reduction in embodied emissions over the 60-year life cycle. This is a good option for single-family residential because you have structural requirements that are more modest compared to taller structures, so you're able to reduce cement content and still create a very durable, long-lasting structure. Another strategy for optimization was to look at reducing wall thickness, reducing the concrete core of the insulating concrete form assembly from 6 inches to 4 inches. You would still meet structural requirements, you'd have a cost-effective approach, and you'd be reducing embodied emissions further. And it's not appreciably impacting thermal mass benefits. Again, because of the more modest structural requirements of single-family construction, the thickness of the wall can easily be decreased. Less concrete does mean less thermal mass, but past studies have shown that these reductions in overall energy consumption performance are very slight. For example, one study looked at reducing wall thicknesses from 12 inches to 4 inches, which result in a 1 to 1.5% reduction in overall energy performance. In this case, we'd be going from 6 inches to 4 inches, so the incremental difference in energy consumption would be quite less. Another key finding from an optimization perspective was the use of thicker insulation in the concrete wall assembly. Looking at increasing the layers of ICF foam from their standard 2 to 2.5 inches to 4 inches. 4 inches turns out to be the optimized thickness of foam insulation, which improves performance and maintains cost effectiveness. Beyond 4 inches, the value of the carbon emissions are offset by the increased material costs. The optimized foam, or the increased thickness of foam, increases annual energy savings. In Chicago, that would result in a 7% increase in annual energy savings by increasing the foam thickness to 4 inches on each side of the wall. And in cooling climates, the annual energy savings would be somewhat smaller, but still representative of an improvement over the 2.5 inch thickness of standard ICF foam construction. A future strategy for optimization will be increasing air tightness, and this represents the greatest potential for additional improvement. Improving from average to tight construction would result in a 23% total savings in operational energy. Going from loose construction to tight construction results in over $300 in energy savings per year. And that's why MIT is looking to the future to determine and understand more effectively the benefits of air infiltration and ways to improve air infiltration reductions in concrete homes. Let's look now at multifamily residential impacts. Again, looking at overall energy consumption on an annualized basis in the United States, multifamily construction consumes 20% of overall residential energy consumption. Again, just as we saw in single-family construction, there have been reductions in heating and cooling consumption over time because of more stringent energy codes, but plug loads caused by increased use of appliances and electronics have offset those savings. So again, in the multifamily market, we can affect better efficiencies and reduce overall environmental impact through LCA. We were comparing wood frame and concrete again, only differing the exterior wall systems, using 4-story structures, 8 units per floor with slab-on-ground foundations. The study looks at the differences between wood frame and ICFs based on the quantity of insulation in each wall assembly and the impact of thermal mass. Just as we saw with single family, the study does not look at differences of air infiltration. The comparisons assume that air tightness is the same for both the wood and the ICF structures. Air infiltration for multifamily residential is even less understood than it is for single family. So again, MIT will be examining this issue further and will have more conclusive results when better data are available. Key findings: when we look at embodied emissions based on pre-use phase and end-of-life phase, again, concrete will have higher embodied global warming potential. In Chicago, the difference is 27%. In Phoenix, that difference is 31%. But again, this phase only accounts for a small portion of overall global warming potential over a 60-year service life. When you look at the full service life, you're looking at greenhouse gas emissions of 2.8 to 5% less for concrete versus wood frame. When the entire service life is considered, the story changes considerably, just as we saw in the single family example. Concrete multifamily buildings use 5 to 8% less energy than code compliant wood frame construction. And again, the durability of concrete would result in those savings increasing beyond that 60-year service life. From an optimization standpoint, the study looked at increasing the use of supplemental cementitious materials in the multifamily construction, increasing from 10 to 50%, which would result in an 11% reduction in embodied energy emissions in multifamily construction over 60 years. Finally, let's look at the commercial impacts. Commercial buildings account for 18% of overall annual energy consumption in the United States, which represents approximately 35% of total electrical consumption. This study looks at only the differences between steel structural frames and concrete structural frames in commercial office construction. So the exterior wall assemblies are identical, the floor-to-floor heights are identical, and the structural bay dimensions are all the same. Typical office construction of 12 stories, 500,000 square feet overall, with 40% glazing was used for the study. From the standpoint of embodied global warming potential for commercial structures, the concrete structural frame produces no greater embodied global warming potential than comparable steel frame construction, even with the extensive end-of-life credits that are realized by recycling over 90% of the structural steel frame. It's not enough to overcome the increased consumption that happens for the steel frame structure during the use phase. Overall emissions, the concrete structural frame produces no greater greenhouse gas emissions over the 60-year service life. There's actually a 2 to 3% energy savings realized when you use a concrete frame versus a steel frame in a commercial structure. When looking at the full study, you will see the energy savings broken out into those for the steel construction and those for an exposed concrete structure and one with finishes. When the frame is covered with finishes, it somewhat reduces the overall thermal mass benefit of the concrete structure. So when you have an exposed concrete structure, you're realizing a full 3% savings. When you wrap that structure, that concrete structure, in finishes, you're going to reduce those savings to 2% compared to the steel frame example. With emissions, you're looking at a 1 to 2% savings in global warming potential emissions using a concrete frame versus a steel frame. When looking at optimization, there were 2 factors studied. The increased use of supplemental cementitious materials in the concrete frame would improve overall environmental performance slightly over a 60-year service life. More exciting was the study to look at the active use of thermal mass capability of concrete slabs, which could result in significant savings in cooling climates. By pre-cooling the slabs, the many slabs in, let's say in this example, a 12-story structure, by running chilled water through embedded water piping, you're cooling down those slabs in off-peak hours, and then those slabs are able to absorb heat energy during the day, which results in a 25% energy savings in Atlanta, Georgia, and a 19% savings in Phoenix, Arizona. Future research by MIT will work to investigate this further to look at the viability of this type of approach for larger commercial structures. So in summary, we're looking at a study which attempts to provide comprehensive full life cycle analysis, examining materials within a whole building concept, striving to provide full transparency and allow for ease of replication, to promote the development of an open and easily repeatable LCA process for buildings to set precedent for future LCA work. It looks at a full life cycle to get a complete and accurate scope of impacts. On the residential side, the concrete wall systems have higher embodied energy than comparable wood frame, but that impact of embodied energy accounts for only 2 to 12% of overall global warming potential. Over the full 60-year service life, concrete structures versus frame structures have lower overall emissions and consume less energy compared to current code-compliant wood frame. The comparison was based on the quantity of insulation and thermal mass in the wall assembly. Future studies will look at the impact of air infiltration. On the commercial side, the concrete structural frames showed no greater global warming potential and do not consume more energy than comparable steel frames, and will actually result in slight energy savings and emissions reduction compared to steel structures. So that completes this presentation. For a full copy of this study, along with summary fact sheets as well as more information about the sustainability of concrete, you can visit the Think Harder website. And with that, thank you.